good. So I make it in two parts. I make a presentation on PowerPoint, and then in the second step, I make a demo of the simulator, one of the simulators we have.
Can you make it full screen, please, Patrick?
I'll try. But do you see the small one? You see the small screen? Do you see a better screen?
Yes, this is better.
Yes.
Yeah.
Okay. So who is Clearsea? It's a French company with 4 offices in France. The headquarters are in Aix-en-Provence, and then we have 3 other offices, one in Lyon, one in Paris, and one in Strasbourg. We are 130 people, more or less. And there are 2 main businesses. One is related to safety solutions. And the company is building safety critical systems, so software up to seal form for railways and other industry. And it is using in its tools and methods a lot of formal methods to make studies or to make code generation, for example, for CBTC applications. And the second branch is ERTMS solutions. And this comes through ERSA, which has been acquired by Clearsea in 2018. And ERSA is doing DMI software, for example, SIL2 software, and also simulation tools for testing and training. And there are 3 families of testing tools. We have tools for testing, for example, testing of onboard systems, testing of trackside systems, either RBC alone or RBC combined with interlocking. Combined system with for testing at the same time onboard and trackside, and also track train integration and interoperability tests. Second line is training for engineers or training for train drivers, either a single driver or multiple drivers in parallel. And the last category is studies. Studies, let's say in the first part of projects, making proofs of concepts, studying operational simulators, situations, studying parameters, studying braking curves, and so on. And what are the main characteristics of our simulation tools? So we are always fully compliant with the norms. And it's not only for nominal cases, which is a lot done in training, but also in many degraded situations. We make a very accurate simulation up to the level of bits for example, balise telegrams, so very accurate. And we have a decomposition of into functional modules with all interfaces combined with the subsets. And this has an interest is that we are not simplifying things. We are doing like a real system. So we can use, for example, direct project data in the tools. We can instruct train drivers, but also signaling engineers, and we can replace simulated components by industrial components. This is the V model which I was given this week about your project, and the question was where could we provide simulation tools? So ahead of projects, we could do for simulation of operational situations. Then for testing, after let's say when the system is being produced, could be done here for testing, and then at the end, before it's in commercial operation, training, because training is mainly at the end of the cycle. So summary of the simulation tools we are doing for studies and training. For single train, it's the operational simulator. For multiple trains, it's a traffic simulator. And for testing, we can test the onboard system with an OBU test bench. We can test trackside system with an RBC test bench. And we can also test both combined with an IOP test bench. There is a RBC test bench which we have provided to ProRail on the Amsterdam-Utrecht line a few years ago, as an example. So the operational simulator is the smallest simulator. It runs on a laptop. it's small but very powerful because there is an EVC simulator inside, and it is fully compliant with the norm. This means that you can test any situation, injecting any packet, any telegram, and you can see the result. There is also a DMI and interfaces with all trackside components. And the way it works, if you have to define scenarios, which you are putting events like, of course, the balise messages, the loop, infill loop, or radio messages, and you decide to inject this according to conditions, and you can also inject, for example, change of signal aspects, change of point position, and so on. This is all defined offline, and then when you run the simulation, it will be executed in real time. You have EVC here in the middle, which can be baseline 2 or baseline 3, and connected to a DMI, and connected to a train dynamics, which is independent from the EVC. And this is important because then you can have parameters of the ETCS having a knowledge about the train and the train behavior, which could be different. And this could lead to several degraded situations, which can be studied. So it can be used for training for drivers, of course, but also signaling engineers, as I told already. You can, there are some options in this simulator. For example, you have the replay function, means that you have done a scenario manually, you store it, and then it can be replayed without intervention to study what happened. You have context management, which means that at a certain time you make a snapshot of the situation and you store it, and the next time you can start from this situation. So this is very useful for training. Then you have the implementation of some STMs. We have done the STM for RTB-EG, for example. And we can also, for training, connect the 3D. We have a simple, let's say, the view of the track is a lateral view, as you can see, but we can also connect an external 3D to make it more realistic when it is needed in projects. Now, the next simulator is for traffic. It's a traffic simulator where we simulate the complete line. So all the components of the trackside part, interlocking, RBC, multiple RBC, automatic route setting. We simulate the track topology and the signaling objects, and all the trains which will be running on the line. And this can also include operational simulators, one or more, with 3D or no 3D. And here on the right side, you see an example where it's a room, it's in the Netherlands at STC with 7 operational simulators running in parallel, and the instructor with preparing scenario and executing scenario in real time. For example, sending a new movement authority or injecting errors to see the reaction of the trainees. And this tool it's not only usable for training, but also for other things like research, line capacity, test environment for conflict resolution system, and so on. Now I go to the testing of systems. So we have a tool to test the onboard system. So you install it here, and then we inject all information around the interfaces according to the subsets. And we can work either with subset 94 or with subset 111.2, because this is the second possibility. And it's used by the ERTMS laboratories and used by some industries for their test, if they want to make tests independent from their own laboratories. Here are some examples of this OBU test bench. And here an example in Switzerland, where we provided it as an example. RBC test bench. And this is taking the traffic simulator and removing the RBC and interlocking from it to replace those components by real industrial products. This is what we did for this ProRail project. And for example, here on the interface with trains, we work with ISDN and Euroradio. And on the interlocking side, we work with proprietary protocols because there is no standard here. And this is used, for example, it's used by ProRail, but it's also used by Thales in a product named TVS. So there are about 20 instances of this product used in Europe. And the number of trains which can be connected is currently 60. And each train inside has the full function of an EVC. So it's a very, very powerful system. And it's used also for replication of lines, because you make a project, you have RBCs, you have interlockings and traffic management systems to install on a track. But you take these products and you interface them with a simulation environment, and you can replicate this line in the lab. And this is also a very, let's say, very powerful way to test and to replicate problems and to analyze situations. So now I have finished this part. I will make a demonstration of the smallest tool. So it's working on a laptop. You can see there is a lateral view. The train is at here, and the view will move, and you have the DMI here, a small desk, and you can see optionally, if you want to study this, you can see the braking curves. So now I will switch to the demonstration. If it works. Do you see a screen with a blue background?
Yes.
Okay, this is now I am now on the server, and I've started one of the simulators. And the first tool is the scenario controller, which I will show you. You have a list of scenarios which have been created offline. So I'm taking an example, level 2, start of mission. I click here, push start. So the system is off at the moment, and the train is here. You see a view of the track. You see, for example, here a marker board. Here in the middle, you have the DMI, which is off at the moment. And on the right side, you have a small desk to drive the train and to control the desk. And here at the bottom, you have some other small windows to get information. So I have to understand that it starts, everything is called, and the EVC is a state machine with many interfaces, and I'm animating the interfaces around the EVC. So I'm switching on the system. This is this button. I can see a lamp here at the train, which is on. And then I open a cabin. And when I open the cabin, the DMI pops up and shows the driver ID screen. And I can either enter some value here, or I just select the current default value, which is 0. It's good for this. I can see also that we are starting in level 2. This is part of the scenario configuration, so you can decide how you start, and if you know where you are or not, what is the distance traveled from a last balise group, and so these are all parameters which you can set in the scenario. Because it's a level 2 line and everything, the data are not lost. A connection has been established. I see here that the connection is established. Here I can see the train speed. I can select a shunting movement or a train movement, but to make a train movement, I need train data. So I will click here, and you see the start button is not available for the moment. I push here. I will take the default value. The value entered by the driver or confirmed go to the EVC, come back, and the driver has the last word to say he agrees to them. I will agree. Otherwise, I have to validate again. So I say yes. you see also on the top of the trains, let's say some circles. This is symbolizing the fact to send or receive a radio message. So train running number is the next parameter to enter. And you see the train running number has been sent. Now I see the start available. I push here. When I push this, it means in level 2 that movement authority request is sent by the EVC to the RBC. And when I push start, you can observe here that the message is going out from the EVC, and then you will see a return from the RBC. And I received a movement authority to drive in on-site mode. So I click here, and the system will switch to on-site mode. You see the mode here. If at the beginning, if I'm not familiar with the system, it may be difficult to understand what is the exchange of data and so on. And there is a specific debugging window, which I can call here, and then I can see entry of driver ID, try to establish a critical connection, etc., message exchange with the DMI, with the radio system, and so on. I can see everything. Okay, now I can drive. I have a traction brake manipulator. You see the train speed changing. You see that the train is not moving, but it's a landscape moving. It's easier to do in simulation. So I have decided in the scenario that it will be in on-site because there could be another train in the same section. So here I see the group of 2 balises coming. On-site, if I'm in on-site, my speed is limited. The speed can be a national speed. Maybe it's here 60. And this can be changed, of course, because you can transmit the national values also anytime. So I continue to drive. So it could be, okay, I received now a confirmation, a Taft, and I have to look if there is no train between where I am and the marker board. It's the case, so I confirm. And the RBC sent movement authority in full supervision. You can see here, full supervision. And you see also the planning area here. And you can also see optionally the braking curves. Either it's in parallel to the DMI, or it substitutes the DMI. And you see the braking curves, how it works. You have the braking curves. Well, these are speed limits in the sailing speed monitoring, as where we are at the moment. And here you see what is going to happen when we are braking to a target. I have the function pause, which is interesting because there are too many things happening at the same time. So the train is not a point; it's an interval. You have the estimated front end position, but you have also the maximum and the minimum, and this is increasing over time when you're passing balises. And there is a model to simulate the odometric error. And you can see here, you have the supervision limits. So this is the first yellow here, the bar here means this yellow bar which is on the DMI. And these bars, indication limit and permitted limit, warning limit, and so on, are calculated in iteration mode, so several times per second. And this has been one of the changes in baseline 3. So there is not a calculation of braking curves, but more supervision limits to be observed. Okay, no, so but you see when I freeze, when I make a pause, it's easier to understand what happens, to explain it. It's very good also for understanding how it works. So I'm go out from pause mode, remove the braking. So this is a simulator, and it's for a single driver, and you can simulate everything which is in the norm. So it's very powerful. So I'm stopping it here. Maybe I just show an intervention. We passed the indication, and then we passed the warning, and we passed the intervention curve. So I'm going to stop here just to show you that it's very realistic, to show you how we work in the scenario editor. So I'm just stopping it. I have opened a scenario with the train is here. Train is here, it's yellow, and you see balises here coming, and you see a signal. I will click on the balise to show you the content. I have 2 balises in this group. I can edit here. I see the header of the balise. I see the different packets, 12, 21, 27, 80, because there was a switch to LS mode in this scenario. If I want to add some packets, I can simply look at the list of packets. I take, for example, this one, move it here, click here, and I see the variables. And if I stay a bit on it, you see the definition, like in the SRS subset 26. So this I can do for any packet, any telegram. I can do it for loop, for radio, for balise. So everything which is in the norm can be tested. Okay, this is to show you the accuracy of the system. And then a second balise in the group. Usually we put no content inside, but they have the same number. NIDC and NIDBG are the same for both. This means that they are in the same balise group.
Patrick, can I interrupt you for a second?
Yes. Yeah.
There are 2 minutes left before you are pulled back to the main session.
Yes. Then I stop for questions. Okay, I have finished.
Patrick, I got one question for you.
Yes.
It's Carl.
Yes. Hello, Carl.
Hello. The RBC behavior, what you have in the simulator, is that adjustable to the RBCs we use in the countries?
So in this simulator, which I have shown, it's not really the RBC, it's only the messages. So we send the messages, we decide to send as messages, so we must know where it comes from. So it could be look at how it works in the Netherlands and try to simulate this.
Yeah, because we get in Holland a smart RBC who gets this information from the interlocking system, but has to update with some messages, and that's what I'm looking for. You understand me?
Yes, okay, but maybe this should be outside this discussion, because it may be long to find an idea. But we have also an RBC simulator, you know, yeah. But the behavior could be different from yours. Yes.
Okay, thank you.
But I think if you send me an email, I try to study this. It's difficult to answer.
Because the RBC behavior is not in the subset, only the text message in the subset.
Yes, exactly. Yes.
Thank you.
Okay, you're welcome.
I don't have questions anymore, so for me it's okay.
So, and we finish at 10 past 11. So we have finished actually.